Welcome to the AI Research Roundup. I'm Alex. Today, we are looking at a paper trending on X, published on November 25, 2025, just 2 days ago. This paper introduces a method called soft adaptive policy optimization that replaces brittle hard clipping in reinforcement learning fine-tuning with a smooth, temperature-controlled gait, leading to more stable training, better sample efficiency, and higher pass at 1 accuracy for large language models, including mixture of expert systems. The paper is titled Soft Adaptive Policy Optimization, and as we will see later, the implications for large-scale model training are quite significant. Alright, Figure 1 contrasts hard clipping with the new soft gait under positive advantage. The left panel shows how the surrogate objective grows with the policy ratio, where hard clipping flattens past a threshold while soft gaits keep rising smoothly. The right panel displays the corresponding gradient weight, which forms peaked curves centered at on-policy updates. Higher temperature values make these peaks narrower, so updates stay tightly focused around safe policy ratios. So, while Figure 1 focused on the shaping of the gait, Figure 3 presents evidence that the theoretical assumptions actually hold in practice. The left panel shows that token importance ratios are extremely concentrated around 1, which means most updates are nearly on policy. The middle histogram reports that per-sequence log ratio variance is tiny, mostly around 1,000th. The right scatter plot compares this variance to the derived bound on sequence-level deviation, and the points stay tightly under the linear bound. Well, the previous figure had already hinted that the theory should match practice, and Figure 2 makes that match very explicit. The left histogram shows that token importance ratios cluster almost perfectly around 1, so most updates stay very close to on policy. The middle plot reports that per-sequence log ratio variance is tiny, on the order of a few thousandths. The right scatter plot compares this variance to the theoretical deviation bound, and the blue points sit tightly under the dashed line, confirming that the bound is sharp yet safe for training stability. Alright, the previous figure supported the theory, and Figure 4 now shows what this means for actual training runs. The top left panel tracks training reward over gradient steps, where the blue soft adaptive policy optimization curve rises smoothly and stays high, while the green and yellow baselines wobble and the green one collapses sharply. The remaining 3 panels report validation accuracy on different math benchmarks, and the blue curve again remains stable and ends higher. This pattern indicates that the soft adaptive gait not only avoids catastrophic crashes, but also converts the same data budget into better final reasoning performance. So while Figure 4 compared soft adaptive policy optimization to other algorithms, Figure 5 examines how different temperature choices affect that same method. The 4 panels together show that setting the negative temperature slightly higher than the positive one keeps both training reward and validation scores rising smoothly. Using equal temperatures stays competitive, but eventually collapses, and making the negative temperature lower than the positive one causes very sharp and early crashes across all benchmarks. So, after exploring temperature effects, Figure 6 shows how the methods behave on a large vision language model. The left panel tracks training reward over gradient steps, where the blue soft adaptive policy optimization curve edges above the green and yellow baselines across the whole run. The right panel reports aggregated validation score, and the blue curve again rises higher and more steadily. These twin trends indicate that the soft adaptive gait converts the same compute budget into both better training efficiency and stronger generalization. Soft adaptive policy optimization shows that replacing hard clipping with a soft, temperature-controlled gait makes reinforcement learning fine-tuning both more stable and more sample efficient for text and vision language models. The broader message is that smoother, token-aware trust regions can unlock safer large-scale training. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.